in session 3 of day 5. So we have our speaker, Dr. Manoj Chanda, with us right now. So I'm going to briefly introduce him with the participants. Dr. Manoj Chanda graduated in Electronics and Communication Engineering from the Kalam Government Engineering College in 2005. He obtained his MTech degree in VLSI and Microelectronics from Jadavpur University. He completed PhD in Engineering from ETCE Department, Jadavpur University in 2018. At present, he is working as Assistant Professor in the Department of ECE, Meghnad Shah Institute of Technology since February 2006. He is a senior member of IEEE and is currently member of IEEE Electron Device Society and Solid State Circuit Society. So Dr. Chanda is co-founder of IEEE Student Branch and Electronic Device MSIT Student Branch Chapter. At present, he is the chapter advisor of Electronic Device Meghnad Shah Institute of Technology Student Branch Chapter. Also, he is the Vice Chairman of Electronic Device Kolkata Chapter. His current research interests span around the study of analytical modeling of nano-dimensional device modeling, low-power VLSI design, SPICE modeling of nanoscale devices, biosensor, gas sensor, AI, ML, VLSI, etc. At present, Dr. Chanda is also serving as the member of IEEE Region 10 Conference Quality and Management. He has published papers in referred international journals of reputed publishers like IEEE VLSI, IEEE TED, IEEE T Nano, LCVR, IET, Spinger, Willy, to name a few. He is the reviewer of many reputed international journals and conferences like IEEE TCAS, IEEE TVLSI, Solid State Circuits LCVR, Journal of Computational Electronics Spinger, International Journal of Numerical Modeling, Electronic Networks, Device and Fields, WILI, International Journal of Electronics, Taylor and Francis, etc. He is the recipient of University Gold Medal in MTech from Jadavpur University in 2008. One of his projects was selected in top 10 VLSI project design category, including BTech and MTech, in all over India, organized by CADSI's Design Contest, Bangalore, India in 2010. He has organized IEEE VLSI DCS 2020, IEEE EDCon 2018 as General Chair or Co-Chair. He also delivered 12 IEEE technical talks in different IEEE conferences, seminars, and FDPs. So, on behalf of organizing committee, I welcome you to this event, sir. Now I am hand over the session to you. Please, sir.
Okay. Am I audible?
Yes, sir. Yes, sir. You are audible.
Yes, sir.
Okay. Thank you, Dr. Jadhav Chandadas, for this nice introduction. First, I would like to thank Maulana Abul Kalam Azad University of Technology for organizing such a useful STTP program in association with AICTE. I am sure that all the attendees will be immensely benefited after this program. Thanks a lot, Madam, for this invitation. Myself, Dr. Manoj Chanda, Dr. Jadhav Chandadas has already introduced me. So, at present, I'm working as assistant professor and head of EC department, Meghnad Shah Institute of Technology. Also, I'm serving as vice chair in IEEE Kolkata chapter, and also I'm working as a member in IEEE Region 10 Conference Quality and Management Committee. Today, I just want to discuss that quantum nanosensors. Mainly, I'll discuss the sensors which are very much related to that disease diagnosis, because we know that the importance of disease diagnosis in recent days because of this COVID pandemic. These are very much important and relevant. So With this, I just want to start my talk. If you have any questions, you can ask me meanwhile, or at the end of session, you can also ask me. So, just let me. Okay, is it visible? I mean to say.
Yes, it is visible, sir. It is in full view mode. First slide show.
So these are the outlines of today's presentation. First, I would like to highlight the sensors, more specifically different sensors, nano sensors, which are available. Next, I will highlight the issues of biosensors and how can you use MOSFET, or why should you use MOSFET as a biosensors. Next, few MOSFET biosensors I would introduce. Here, I will also like to share few of our works which have been published in ITP, transactional electron devices, and T-nanos. And later, I will show one silicon nanowire MOSFETs, where MOSFETs and silicon MOSFETs and that silicon nanowire both have been fabricated on a single chip to design that hybrid biosensors. And finally, I will brief that future scopes, possible scopes of this nanosensing domain related to that biosensing or that disease diagnosis. And finally, I will conclude. So, first thing is introduction to nanosensors. I hope all of you are familiar with that sensors. Must be. Basically, sensors are some devices which can sense simply. So here we are discussing, or we are talking about nanosensors. So nanosensors, this must be able to sense that a nanoparticles or nanospecies. Now these nanospecies or nanoparticles, this can be some kind of antibody, some kind of this is some kind of DNAs, proteins, enzymes, or some kind of biomolecules, etc., etc. So these sensors or nanosensors, they must be able to sense this kind of nanospecies or this nanoparticles. Even it can also sense that nanoparticles also. And what will it do after sensing these particles or nanospecies? They will produce some kind of signal which will be further processed by some smart devices. And what's about the dimension of the sensors? As we are sensing some nanoparticles, it must have some nanoscale to macroscopic level of dimension. I mean to say simply nanometer to micrometer. That should be the dimension of these devices. So basically, we are using small dimensional sensors, nano dimensional sensors to sense nanospecies or nanoparticles. Now, if you ask what are the application of these nanosensors, then there are plethora of applications. I mean to say, you can apply nanosensors in each and every zone, in each and every region. These are few, I mean to say, most prominent applications I just have listed here. But apart from that, you may consider defense or forensics. Even on these parts also, you can use these nanosensors. So if I brief some applications, these are mainly pollution monitoring. More specifically, you can use that nanosensors to sense that gas molecule. Suppose you want to sense that toxic gases, and then you can use some nanosensor to sense this or to detect these toxic gases. Even let's take an example. So you may use a CNT or carbon nanotube, which is a nano-dimensional device, to sense that NO2. How? When NO2 will be sensed, or when NO2 is absorbed, then what will happen? NO2 or it will strip an electron from that CNT, and then CNT will be less conductive. So basically, the conductivity of CNT will be less after absorbing that NO2. Similarly, there are agricultural part where you can also use that nanostructures to make that agriculture smarter. How? Say you can consider these nanosensors to detect different kind of pesticides, fertilizers. Even it can detect that soil humidity. Okay. Also, it can it can identify crop pest. These are very much important to make that agriculture smarter. I mean, this to get more better results, we can go with that nano sensor for sensing this kind of fertilizer or these pesticides or the other parameters, say humidities. You can also use these nano sensors for food safety also, because nowadays formaldehyde, this has been used extensively for, to make that to continue that freshness of these foods, or sometimes we add poisons to that vegetables. So these are very much harmful for our body. So if you can use these nano sensors, then nano sensor can detect pathogenic bacteria. It can detect that toxic elements, adulterant vitamins, so dyes, fertilizers, pesticides, which might be added with that food. Also, it can check that freshness of these foods. So you may also add that nano sensors to continue that, to get that, to continue this food safety. So these are a few applications. Even you may also measure that food freshness using these nano sensors. Okay, so using nano sensor, you can measure the freshness of that food using some time dependent and oxygen indicators. So these are few applications which are very much efficient for the betterment of our society, for the betterment of our health. Besides, I must mention one thing which is known as nanobionics. Here, this is the one of the most emerging application of that nano sensors. In these nanobionics, what we do, we just integrate, or we just create some interfacing in between biological part of that plants and in between some biological part of that plant and non-biological nanostructured element. So that interfacing is the main aim of this nanobionics. I can share one example. Recently, MIT engineers have embedded that carbon nanotube on spinach leaves and make this spinach as a sensor. So now that these spinach leaves can sense the explosive, can detect that explosives, and they can send the signal to the nearest smartphones. So that's the importance of nanobionics. Even there are lots of applications, but this is one of the most emerging field. You may use a single wall nanotube and chloroplast assemblies, and this assembly can enable higher rates of deep electron transports in a plant. So through a mechanism known as photoabsorption process. So they can enhance, or they can enhance that biological process. Also, they can convert if they can convert these trees into sensors also. So these are most emerging, but the most important thing is that medical technology. You can use that nano sensors starting from a drug injection to detection of virus, detection of enzymes, detection of bacteria, etc., etc. So the most important and the most dominating field is this medical technology, or diagnosis of say diagnosis of disease, or even say design and fabrication of some bioimplantable devices inside our body to control that operation for the betterment of health. So these are few applications of nano sensors where we are using nano sensors extensively, and these are all emerging fields. And these all the fields are very much relevant for the betterment of our societies. So that's why I just highlighted this part. Obviously, there are too many applications which I skip intentionally because of shortage of time. Now, these are the different nanosensor types, which are very much related to the last slide. Say, you can use nanoparticles and nanoclusters as a nanosensors. So simply a particle can be used as a sensors also. Simply nanoclusters or nanoparticles that will be used to sense some another nanoparticles. Nanowires, nanofibers, nanoribbons, carbon nanotube. This can be also used as a nanosensors. Graphene or 3D materials, say MOS2 or WS2. different metal organic frameworks or MOF. These MOFs can be used as a nano sensors, especially for detection of gas molecules, and also that bulk nanostructure FET. Basically, you can use graphene to design a FET. You can use MOS to design a FET. You can use some other 2D materials to design a FET. Even C5 materials can be used to design a FET. A simple silicon can be used to design a FET. So there are lots of possibilities to in this design of FET. I mean, there's a lots of materials are available for this FET, and this FET can be fabricated or can be designed easily, and we can get better accuracy also from that FET if you can design it perfectly in nano dimensions. Obviously, there will be some issues that I will discuss later in my slides. Okay, so next thing is this. Now I will highlight mainly these things with some examples. I won't go in deep of these nanoparticles or nanoclusters or nanowire, nanofibers, CNT based sensors or graphene based sensor or MOF sensors. I will just highlight, or I will concentrate on that bulk nanostructure FET. How you can use bulk nanostructure FET to detect some protein, to detect some DNA, or from some other nanoparticles. That I will discuss mainly. But here I just want to show few application of this just to give some idea about that recent development of these things. So let's start with that nanoparticles and nanoclusters. In left side here we are using some gold nanoclusters. Look, here we are using to consider these are test tubes. So here we have protein with gold nanoclusters in absence of bacteria, obviously. This is mainly fluorescence sensors, and here the intensity variation that will be detected as final output signal, and this will convey the information regarding the presence or absence of bacteria. Okay. Sometimes it will show some different colors as an output. So here what we are getting, say this is in absence of bacteria, and in presence of bacteria we are getting these different colors. And what's about that intensity? Look about that, in presence of bacteria that intensity falls. So here gold nanoclusters, these are used as a sensors. So this can sense the presence of bacteria. They will change their colors, and finally we'll get less intensity. Also, if we consider different proteins, HSA, LF, LYZ, VAN, if we consider these 5 different configuration, and in these 5 different configuration, what will happen if you add gold nanoclusters, then these 5 different bacteria will show different colors. Okay, so observe, also going through these colors, we can also identify the presence of bacteria. Even observing this color, we can say, okay, if this is the element, if this is this HSA gold nanoclusters, then this color will give you the idea of bacteria 3, presence of bacteria 3. But in case of these things, what will happen? Look at that color. This is fainted. So I just want to say that using that fluorescent nano sensors, you can use this gold nanoclusters element to sense the bacteria. Okay, and you are getting some intensity variation at that output. Similarly, here we are using some quantum dots, which is also which can be considered as nanoparticles. So that quantum dot, the dimension is in few nanometer range. So here CDT as ZNAC, these quantum dots are used here. And look at that spikes. These spikes are basically receptor. These spikes are basically made of GSH and MMA, glutathione, and glutathione, and that markup to acetic acid. So these things are basically here at the surroundings of that quantum dot. These are basically receptor. What is the function of this receptor? This will trap that analytes which you want to capture. So here, suppose this is CO2 plus, we want to capture this thing. So what will happen? This will be captured by this GSH or MMA, and finally we will get this immobilized quantum dot. So these are some nanoparticles and nanoclusters examples. Also, this one is very much significant. This is basically SPR, or surface plasmon resonance structure. Why this is important? Because here we can get some level free detection. This is real time and the sensitivity is very high. Now, what is level free detection? Basically, level free detection stands for we don't need to mark that bacteria or biomolecules. Okay, we don't no need to label them. Without labeling, we can easily detect the presence of this bacteria or these biomolecules or these nanoparticles. Now, what is this SPR, basic or surface plasmon resonance? This surface plasmon resonance, this is basically, this term signifies this total mechanism will occur in the surface, in surface or something. Plasmon, this plasmon wave will be formed, and resonance means simply this is just nothing but a resonance effect, where phonon from that incoming light, they will interact with that conduction band electrons of that nanoparticles. Okay, so this is basically a resonance effect, and this resonance effect will produce some plasmon, and this plasmon will propagate, and because of that our output intensity of that light will differ. So if I want to say in detail, then I can say that this SPR, this is just nothing but a resonance effect due to the interaction of this conduction band electron from that metal nanoparticles with the incident photons. Basically, when you give some light rays, and then there must be some photons. These photons will interact with this conduction band electron of the nanoparticle, metal nanoparticle. Now, this interaction, obviously, this depends on the size and shape of that metal nanoparticles. If the size differs, then what will happen? This interaction will also be affected. Now, when SPR occurs, this SPR occurs when this polarized light, this is that polarized light, when this polarized light incident on that surface and strikes, and this electrically conducting surface. Why I'm talking about this electrically conducting surface, because this is look here, this surface is electrically conducting surface made of that gold nanoparticles. So what will happen when polarized light strikes that electrically conducting surface at the interface of two media? These are the mediums. Now, when they strike, then they will generate some charge density waves. These are called basically plasmons. And when these plasmons will form, then this output intensity, this will vary. So that is why this effect is known as plasmon reference, surface plasmon resonance and SPR. This can offer very good sensitivity. But it has also some disadvantages, because here we need very thin film to get better result, to get higher sensitivity. And obviously, as we are dealing with light, so change in refractive index or RI, this can add some extra signal which can be treated as noise. Also, mass transport can affect. Mass transport means here you are inserting some analytes, or here inside this flow channel there will be some mass transport. So sometimes this mass transport can affect this binding of this biomolecules with that sensing surfaces. So these are the few issues which can impose some limitations on this SPR sensors. However, these are very much effective because of their better sensitivities. So now come to that nanowire or nanofiber or carbon nanotube. It has different kind of applications, starting from gas sensing to biosensing. Okay, here look at this. Here I just have given an example of acetone sensing. This is some SNO2 nanofibers. This SNO2 nanofiber, this has been functionalized by some platinum nanoparticles. Now this can sense that acetone. Now you can consider this as gas sensing, or you can also associate this with some potential applications or potential example of some disease diagnosis. Basically, this acetone, hydrogen sulfide, this or ammonia or toluene, these are some volatile organic compound. These are the examples of some volatile organic compound, and they can be considered as biomarkers for some disease, mainly diabetes. These kidney malfunctions, lung cancers. In these cases, this can be used as a biomarkers. So we detecting these things, we can easily diagnose. We can go with the diagnosis of these diseases. Here also, I am just showing one example of flexible hydrogen sensors. Is WCNT, that is single wall carbon nanotube decorated with palladium nanoparticles. So these things also can sense that hydrogen gases, and this is made of carbon nanotube. So carbon nanotube, here we can use this carbon nanotube for gas sensing. Say another structure is this. This is FET-like structure where we have source drain, where we will apply some potential to create some field. This here, this CNT can use to sense that gas molecules also. Here we are using some single wall carbon nanotube decorated with palladium and palladium nanoparticle to sense that hydrogen gas. Here we are using some FET-like structure to sense that gas molecules. Look at these examples. The similar structure, almost similar structure. Here we are using single wall carbon nanotube to sense that biomolecules. How? Now look at this look at this carbon nanotube wall. Now if you can functionalize this wall with proper receptor, then this receptor can trap that analytes easily, can trap that target biomolecules, and can give some variation in final current. Observing this, you can say, okay, this confirms that presence of biomolecules. So here I'm just I just told you that you can use that carbon nanotube as a gas sensor. Besides, you can also same carbon nanotube, almost similar structure, for biomolecule sensing, so or biosensing. So this is a potential candidate. This carbon nanotube, this graphenes, 2D material, these are the potential candidates in nanosensing application. They have too many advantages. Besides, also they have some disadvantages also. Otherwise, we might get this kind of things in each and everywhere. But however, lots of researchers are going on to eliminate these issues. Finally, within few days, we'll see the application in everywhere. But still, this can be used as a potential candidate for gas sensing to biosensing. Now look at this application of CNT. It can detect not only this, but these are some examples which are familiar with. It can detect folic acid. It can detect some antibody, human EGF, nucleic acid or DNA, aptamers, protein, peptide, enzymes, etc., etc. So this CNT is very much useful. And nowadays, what we are doing, we are just using some. We are integrating that 2D material and FET principles together and sensing this gas to biomolecules. Now again, come to this graphene. As I've mentioned, that graphene is another strong candidate in this zone. Basically, using graphene, you can design non-invasive devices or invasive devices. What does it means? Basically, if we go with that application, I mean to say bioelectronics applications, there are two types of devices, mainly wearable and implantable. So for example, hearing aid is a wearable devices, whereas as a pacemaker is some kind of implantable devices. There are lots of issues and challenges are there, because when you implant any devices inside our body, then you have to keep in mind that toxicity of that devices, the material which you are choosing, how much toxic it is. Because if the material is toxic, then there will be no utility to implementing these devices inside our body. So it can damage your body parts also. So that's why you have to be careful when you are choosing these devices and when you are analyzing the toxicity of these devices for implantable applications. There are some other parts which is wearable, non-invasives. So here I'm just giving one picture. In left side, we are getting some invasive applications. Invasive means which are wearable applications. And in right side, you are getting some non-invasive applications. And these are just pictorial presentation of some invasive or non-invasive applications. So using graphene, we are designing, our researchers, too many articles have been reported. on this design and implementation of wearable and implantable devices. So here, graphene, you can fabricate that graphene on skin just to measure the component of sweat, or you can detect the presence of some compound in that during that sweating. So here, graphene with nanoparticles that can be fabricated on on a skin. This is platinum nanowire functionalized graphene sheet, and this can be used to observe or to detect some movement in our legs. This is some example of graphene layers which can be implanted on that heart wall to measure some or to detect some biomolecules. So these are few pictorial presentation which can show that the potential applications of this graphene in this zone. This is metal organic framework or MOFs. What are these things basically? Here, look at that picture. This is organic inorganic hybrid crystalline porous materials. What does it mean? It has organic linkers and also metal ions. How this will be formed? They will form a regular array of positive metal ions. These are the positive metal ions, and these positive metal ions, these are surrounded by organic linkers. These metal ions will bind the arm of that linkers, okay, and they will form this kind of cage-like structure. This is known as metal organic framework. What is the utility of this kind of metal organic frameworks or MOF? Basically, look at that structure. It has high surface area, and because of this high surface area, they are very much useful in gas sensing applications. Now here I have given one example where sulfur dioxide molecule. So this is SO2 structure, SO2. This SO2, these are selectively taken up by the pores, that MOFs. Okay. So to detect that SO2, you can use that MOF structure. Now I will show some potential MOFs. So these are some potential MOF. Look at this, where you are getting that metal ion. They are holding the arms of these organic linkers. Okay. So these are the structures. Here, look, MOF74, for example, this Mg, NiCO. These are the metal ions, magnesium, nickel, cobalt. How can you, in which field you can use this? You can use to sense that CO2, NOCH4, just to sense this kind of gases, you can use this MOF. Whereas this structure can be used to detect that CO2. Okay. So here also zinc can be used as a metal ion, and this is the organic linkers. You can form these cells, unit cells, MOF unit cells, and that will be used to sense the gases. Let's come to that final part of this example. So this is bulk nanostructured FET. Bulk nanostructured FET, that is bulk means physically we are dealing with three-dimensional devices. Here you can consider this as a nanostructured FET also, because length and width, these will be reduced drastically. Also vertically, it will be scaled down vertically significantly. Nanostructure means dimension is in nano domain, and FET, these principles are basically very much similar to that MOSFET. MOSFET means these principles are very much similar with the FET principle. FET principle means field effect transistors principle. So here we will apply potential at that source end and drain it at two end. When you apply some potential difference across these two end, what will happen? Say the length is L. So V by L, some electric field will be produced. And because of that electric field, some current will flow in between source and drain terminal. Now what will happen in presence of some gas molecules or in presence of some biomolecules? This current, either they will increase or decrease. So you will get some variation in current. Observing this variation, we can say, okay, that biomolecules or bacteria or some DNAs or some proteins or some gases, these are present. So this is related to the variation, the presence of bacteria, presence of nanoparticles, or presence of gas molecules. These will be directly proportional to the variation of that current. Okay, this is potential. This is very much significant in the field of nanosensing, because we know that we can fabricate easily. We can fabricate a MOSFET or we can fabricate a FET easily in a bulk. So what will happen? It will be a cost-effective way. Not only that, as you're familiar with that principle very much, so we don't need to work on it. So we can go for that implementation quickly, and we can use this for different zones. So here I'm also suggesting some sharing some application that this is pH sensors. We can basically measure that pH, as I've mentioned, that what will happen when there is a pH variation, because that current will vary. Okay. So here we are plotting that IV characteristic VDS, that is drain to source voltage of this device, which we are varying. And when we are varying this, we are getting some current in between source drain. Now here for pH 6.3, we are getting this triangle shaped current line. For pH 8.2, we are getting that rectangle shaped current line. So rectangle shaped line. So the thing is, obviously, when we are increasing that pH, the current is increasing. I'm not going in deeper mechanism why with increasing up with that pH, why current is increasing. In some cases, with variation of some biomolecules, that current might decrease. But this entirely depends on the operating principle of this device. But here we are strongly finding out the variation of that current as an output, and observing this variation of current, we can identify the presence of that bacteria or some other biomolecules. Okay. Here, this is FET photosensors, and this is also current voltage characteristic. Look, this is irradiations. So when irradiation varies, here also we are getting different amount of current. So here we are using this photosensor, we are using this irradiation. We are sensing this irradiation, and we are getting that current variations. Hence, this is FET variation, FET nano biosensors. This is simply source drain and the MOSFET. Here, this is the sensing surface. The sensing surface can detect some biomolecules, can sense some biomolecules. And what will happen when it sends some biomolecules, its current voltage relation, IV, will vary also with this. So till now, we are discussing these nano sensors, which are potential application in diagnosis of disease, or you can say identification of biomolecules. Now, if we consider where we are converging, then what we are aiming, the aim is this lab on a chip. That discrete sensors, if we can fabricate all these discrete sensors in a single chip, then we can get different kind of function from a single chip. So when you go through a lab, we can get different kind of diagnosis. So it can measure that WBC, RBC, it can measure the sugar level, it can measure the thyroid or lipid profile, so many things, and that can be done in a single lab. So if we can use different kind of sensors to detect these different kind of proteins or biomarkers, and if we can fabricate on a single chip, then a single chip within a dimension of few millimeter, that can purpose or that can be used instead of a lab. So that is the concept of lab on a chip. And here you just need to keep in mind that you need to fabricate all the parts on a single chip. Say suppose you have a FET biosensors, and this FET biosensors can detect, say it can be used to measure your glucose level, it can be used to measure your lipid profile. So these two sensors, if we can fabricate on a chip, then you can move towards a design of LOC. But if we go with SPR sensors, if you are going with that microfluidic sensors, MEMS-based sensors, also they are very much potential application in this biosensing. Then would it be possible to fabricate everything on a single chip? There will be some issues, because if you deal with that microfluidic channel, there will be MEHD issues, which is known as micro electrohydrodynamic issues. There might be a problem to drive that miscible fluids. There might be some mixing in a chaotic nature. Then also that gas flow, they need larger dimensions. Sometimes liquids can split over the surface. So these are basic issues of that microfluidic channel. I'm not going in deep, but I'm just showing another way how we can design that LOC using that fate-based biosensor or SI fate or some other materials-based fate. So as you're familiar with that fate, and as we know that fate can be fabricated easily on a chip, so we can integrate different kind of fate-based biosensor. There are possibilities, and we can design that LOC for future applications. And once you can design that fate-based LOC, then what will happen? You can provide this kind of facility to a remote place where the people are not able to go through that lab or for that regular checkup, but you can provide this LOC, you can provide this chip, you can provide this IC with some smart sensing measurement system, and they can easily go through that diagnosis at their home without going to that lab, without visiting to that lab. So this will change that picture entirely. But also, besides, I must say that there are too many issues. It's not an easy task to design a sensor, because we know that sensors, especially in nano dimension, because fates are based on basically when you are using some fates or when you are measuring some current variation, this will we are getting this output basically because of the movement of electrons. Now, when you are considering nano dimension, we are forcing these electrons to move through a nano dimension or nano structures. Now, when you confine these electrons within a very narrow space, then electrons will behave differently, and that will be the most challenging work to control their motion or to use them for your application. So these are the challenges. However, hopefully this will be overcome also. The researchers will overcome these issues. So this is our aim, just to design a LOC using that FET or FATES, because we are very much aware with the fabrication flow and we know how to do it easily. But the challenge is to control the motion of the electron in a nano-dimensional devices, and also the sensitivities. So let's go through some applications which will clear this idea. Okay, we can use that FET for our biosensing application, and obviously they are very much, they have we have too many strong reasons to use this FET for this LOC implementations. So I'm moving to that second part where we are using that FET as a biosensor. As I mentioned, that this is cost effective. Obviously, nowadays we can fabricate billion number of transistors on a single wafer, which can reduce that cost significantly. Level 3, if you can use that phase-based FET-based device, then you can go with some level 3 properties. Batch processing, higher sensitivity, better response time. Obviously, this response time is very much significant. When you go for that COVID checking, you won't expect that result after few hours or after 10 hours or after few days. You want to get that result quickly. So that's the beauty of response time. If the response time is very low, then you can get that result within very few minutes or few seconds. But if the response time is very high, then you need much longer time to get that result. So why FET is why FET-based biosensors are why we can use FET as a biosensor? Because FET can be scaled down easily. Nowadays we are dealing with 10 nanometer FET. IBM or Samsung, they are dealing with 10 nanometer, 12 nanometer, 6 nanometer, 7 nanometer dimensional MOSFET. So this can be scaled down. It has been proved. So we know that to detect any smaller particles, we need to be smaller, as we can scale down that FET easily. So there are some possibilities. Let's check. So now I just want to go with that biosensing, because till now what we have discussed, these were some common sensors. You can use that sensors for gas sensing. You can use that sensors for biosensing. Now I'm just I just want to stick with that FET-based devices which can be used for biosensing. So what is a biosensors? Let me divide this into 3 parts. First part, where we have targets and receptors. Second part is the transducer, and the final part is that signal conditional unit. So this part is the first part, where we have target and as well as receptor. To receive a target, we need a receptor. Say we have some antigen. These are the target biomolecules. We need to trap this biomolecule. So what we have to do, we need to put some antibody to get that antigen. Say suppose we have some toxic elements or toxic biomolecule virus. So what we can do, we can put some enzymes, or we can put some DNA, we can put some other protein as a receptor just to trap this biomolecules, or just to trap these target biomolecules. Okay. Even you can detect some explosive material. So as I'm talking about that biosensing, I'm ignoring these heavy metals of this explosive materials. I'm just sticking with these antigens, virus, or these toxic elements, etc., etc. Now the second part is that fate. How it will work? Look, you can use some different kind of transducers also, which can convert this, which can generate some electric signal on basis of some, say, pressure variation, on basis of temperature variation. They can produce some signal. So there are different kind of transducer, different kind of sensors are available, which are working on different principles. But here we are using that fate as a transducer. What is the basic principle? I just already mentioned that. What is the main operation? When this fate identifies the presence of biomolecules, when this receptor traps these target biomolecules, then the conductivity of that fate will change mainly. More or less current will start to flow through this fate. And finally, they will give some current variation. Now, suppose in general, say fate is giving some microampere current. So we are considering 100 nanometer fate, we are getting some microampere current, or say 10 to the power minus 4, a few milliampere amount of current through that fate. Now these 100 nanometer or 200 nanometer sensors, these are giving some variation in current as output after detecting some virus. So the current variation will be in the range of microampere to milliampere. So we can put some op-amp here. We can put some op-amp. We can amplify this current, or that difference, we can put some differential amplifier just to get better gap, or just get better amplification. And finally, after putting, say, A to D converter or a ADC, something like that, we can display the things on some monitor screen. So here I'm just sharing some blocks. So this can be used as a signal conditioning element, because the output of the transducer or output of that fate will be milliampere to microampere level. And this can't be treated directly, because if you consider microampere amount of current, and there might be some noises. So what we have to do, we have to use proper signal conditioning circuits, which can amplify that current properly. And then the analog signal, or this will be processed to get some better output in digital format, and this can be displayed on some monitor screen. So this is the example. This is the example here. This is the fate, source, drain. This is the gate. This gate is amplified just to show that inner part of this gate has been etched, where we can collect that blood samples. Now, in presence of that blood sample, what will happen? Some drain to source or source to drain current, this will vary. And because of that current variation, what will happen? If you can pass through that some signal amplifier, that current or voltage gap, that will be amplified. Finally, if you pass this through some AICTE converter, then we get some digitized output here. So look at this. Hence, we are using MOSFET. We are getting some digital output, and this is a complete example of biosensor. These are the few characteristics of biosensors. What are the functions of and this? And when you analyze a biosensor, you must go through these properties. If these properties are okay, then this is a good biosensor. If these properties are not okay, then you can say, okay, this biosensor is not applicable, because it's lagging in this case. So we can ignore the use. So what are the properties? Mainly selectivity, sensitivity, stability, linearity. What is selectivity? Suppose I'm giving one example of that biosensor, and all of us we are very much aware with that term COVID-19, and that's why we are sharing this PPT in online mode, otherwise it could be on offline mode. So here, this is a graphene-based FET. This graphene-based FET, this is used to detect that COVID-19 virus, or sorry, coronavirus. So what will happen? This graphene surface, this has been functionalized properly. So when it receives that coronavirus or that SARS-CoV-2, then what will happen? You will get some changes in current. I'm giving some example. These are COVID-19 patients. These samples where we have coronavirus. And now when we add this virus with this, when we pass this through the sensors, then what will happen? Look, this is drain source. This is gate. This gate is liquid gate. Okay, now what will happen when we add this virus, or when it detects that virus? Look at this, it gives some different peak for different viruses. Now selectivity is something, suppose you have a mixture of viruses, say there might be SARS-CoV-2, there might be MERS-CoV-2. Now selectivity will isolate that proper one from the others. Look at that peak. Here for MERS-CoV, that peak is not significant, but in presence of SARS-CoV-2, you are getting these larger peaks. That is selectivity. If the biosensor can isolate the worst one or the prominent one from the mixture, then the biosensor is selective. What is sensitivity? Sensitivity means how accurately it can sense, or how accurately it can detect the presence of bacteria. Now suppose here you have 3 biomolecules. I suppose you have 3 viruses, 3 virus molecules. Okay. Now if this device is highly sensitive, then what can happen? Then it might detect the presence of coronavirus. So instead of 3, if there is single virus, still the device will be able to identify or the presence of this virus. Then the device is highly sensitive. I mean to say, if there is any small amount of bacteria or virus, still the device will be able to detect it. That is sensitivity. And LOD, that is level of detection, that LOD is very much associated with sensitivity. The device is very much sensitive, then level of detection should be low. Okay. So the thing is, it can easily detect from a high concentration of mixture. But if the concentration is very low, then how it will react, or what will be the sensitivity, what will be the level of detection? That is the most important thing. Because if you have a, I mean to say, if you have a mixture where too many coronaviruses are there, then what will happen? Too many viruses will bind with this surface. Then there will be significant change in current. That's not challenging. Challenge will come when you are dealing with low concentration of samples. I mean to say, suppose a patient, you have a sample of a patient or COVID patients where the coronavirus or the virus are very less in quantity. But if your device is not sensitive, if the LOD is not lower, then what will happen? Then the sensor won't respond in presence of low concentration of virus. So your device has to be sensitive, otherwise you don't be able to identify that presence of virus. As the output, what we will get, we can say, okay, this patient is okay, but actually the patient is not okay. The quantity of virus or quantity of coronavirus is less. So you have to make your device a sensitive one, and device should be as much as sensitive. I mean to say, it will be able to detect very low quantity of biomolecules. That's the challenge. And another thing is stability. Stability is something which can affect your operation. Suppose, for example, here you are dealing with some current variation with time. Say for MERS COVID, you are getting this very low spike, you are getting very high spike for SARS-CoV-2. But suppose you are varying that pressure, you are varying that temperature, then what will happen? If these peaks are not changing, then it is okay. That means your device or your operation is stable. Otherwise, what will happen? At Puri Sea Beach, you can get one reading. At the top of Darjeeling, you will get another reading. I mean to say, because of temperature deviation, if that affects your output characteristics, then your device is not stable or your operations are not stable. If you go through some pH sensors, which are also very much active in this zone, but if you go through pH sensor, the pH can vary with the temperature or some pressures. So what will happen if there is intense variation of pressure or temperature, then pH sensors will not give same results. You just need to consider. That's why go with that pH property is not a good thing always. So you have to change. You have to measure some different properties, which might not change with temperature, which might not change with pressure variation. And here comes that level 3. Say suppose you have some biomolecules whose pH you know that this or you have some analytes, you know that pH may vary if you vary the temperature or pressure, and what will happen, your stability will be hampered. But instead of pH, if you go with the dielectric constant of this material, suppose you have some dielectric constant of this, you have some fixed dielectric constant of this analyte, but this dielectric constant will not change rapidly with the variation of temperature and pressure. So you can fix with the dielectric constant, and you can use this dielectric, using these dielectric properties, you can measure the presence of bacteria or viruses. Okay, that's the stability. And finally, there is linearity. What does it mean? That response will change proportionately with the concentration of that analyte. It's a simple y is equal to mx. You can consider that y as a output response, x, that is x as a concentration of your analyte. So if we increase that x, what will happen? Your y output response will increase, and if the slope is constant, then your graph is more or less linear. This is linear. This is linear one. And here I am giving one idea of that response time. What does it mean? Look, hence x-axis is some time axis, and y-axis we are getting some variation of current. Del I is the deviation in current. I0 is that bulk current. In absence of coronavirus, there is a I0 amount of current. Now in presence of coronavirus, say you are getting I1 amount of current. So the gap between I1 and I0, that is basically del I. So del I by I0, that will give you basically current sensitivity. So here we are measuring current sensitivity with respect to time. This is very much related to that response time. So look, when the concentration is 100 picogram per mole, you are getting that current sensitivity, better current sensitivity. Okay, but when you are dealing with that 100 femtogram per mole, that current sensitivity is very low because that del I is very low. So that I just pointed out, when del I is very low, this is the challenge. How can you say, or how can you detect the presence of bacteria? And say response time is something. Response time is when coronavirus, you are adding some coronavirus to that graphene sheet, what will happen? Your del I will appear, your I0 will change to I1. Response time, and finally I1 will reach some steady state. So response time, that will be calculated approximately the time during which I0 will change to that steady state value of I1. So this gap will be the response time more or less. So these are the few properties of that biosensors, and this is a good one because it has a good selectivity, it has very good response, linear responses, and it can also detect that picogram per mole within that 300 second or 400 second. It can offer, say, del I by del I0 significant current sensitivity at this concentration. So at this smaller concentration, so we can say this is also, this has very much very good sensitivity. So that biosensor possesses some better qualities. And these are the applications of red biosensor. Also, I have mentioned few diagrams, and these are the zones where you can use that fate as a biosensors. Now here I'm just skipping these things. So this is the pictorial presentation of the properties of biosensor. And also here, I just want to say one thing, that this paper has been published in ACS Nano in last year. And this will give you a complete picture of detection of coronavirus using some graphene FAT. So if we can fabricate these things, if these things, I mean, this fabrication is going on using these devices, then that sensing devices, the cost of that sensing devices will be very low. Simple structure, source, drain, gate, that graphene sheet is used here. And if you want to get the details, I just have these things, ACS Nano 2020. Last year, at the end of last year, it has been published. So you can go through that paper to get that better idea. And this is the same thing. So in presence of SARS-CoV-2 virus, you are getting some response at that output. But when you have MERS, Mars, COVID, you are not getting any responses. That is the selectivity, very good selectivity. And here also response is directly proportional to that concentration. So the device is linear. So this is the relationship. This is the properties of that good biosensors. Now I will discuss some aspects of that FET based biosensors. These FET based biosensors, these are very much available in the literature. Still some researches are going on. I have just considered 4 to 5 papers from the recent literature. Let me highlight few parts. I mean, these are few properties on basis of which we can use that level 3 detection. As just I have mentioned a few minutes ago, you can use the dielectric properties of that biomolecules. Suppose I'm considering biotin, septavidin. You can consider that protein structure of that biotin or septavidin or AICTE, or you can also consider that dielectric constant of this biotin or septavidin, say 2.1 or 2.33. These are the approximately dielectric constant. So you may consider that when you detect that DNA, you may consider some dielectric constant of the, you may consider that protein structure of DNA depending on its base. Also, you can calculate or can estimate that dielectric constant of that DNA 2. You can also find out the dielectric constant of that virus 2. And observing the dielectric constant using this principle, you can design some FAT to detect this. Okay. You can go through that literature, you will get too many things regarding the dielectric constant. Say, for example, if you consider dry protein, if you want to measure, if you want to detect that dry protein, you can go with that protein structure, or you can simply consider 2 to 3. That is more or less average dielectric constant of this dry protein, those which are available in that laboratory mainly. So you can go with the dielectric constant also, and but you have to be specific with the dielectric constant. You have to first measure the dielectric constant of this bacteria or virus, otherwise you won't be able to identify that detection. Okay, now this is the thing. Just a minute. Okay, this is the thing. This is dielectric modulated MOSFET biosensor. Why dielectric modulated? That I will discuss later. MOSFET biosensor, because this is a pure MOSFET. Okay, what we have done here? Nothing except etching of gate. This is gold and chromium. This is the gate structure. This green part, this is SiO2 layer. This is channel, source side, drain side. And this is kept on buried oxide, SiO wafer. Ignore this, main operation will be here. Now what will happen here, we are etching some part of that chromium. Okay, why we are etching some part of chromium? Because we just need to create some gap here. That this gap is known as nano gap. This can be considered as nano gap embedded biosensor, because we are embedding some nano gap here. And the dimension, what will be the dimension? The dimension will be few nanometer, and this height will be also 10 to 15 nanometer, and this length will be 100 to maximum 50 to 100 nanometer. So they are in nano dimension. So what is the function of this nano dimension? This nano dimension or nano cavity these nanocavities can be used to trap the biomolecules. What will happen if you trap the biomolecules here? Look, when you consider that FET or MOSFET, better if I say MOSFET, then that total mechanism, that will be basically capacitive behavior. Okay. If you change that gate capacitance, what will happen? The threshold voltage of this MOSFET will vary. Finally, your current will vary. Here, when you create some gap here, what will happen? Ultimately, forget that trapping of biomolecule. Just think about that. If this gap is filled by chromium, suppose then the capacitance is C1. Gate capacitance is C1. Now you are etching some part of this gate. So a cavity is formed here. And this cavity is filled by air. The dielectric constant is 1. So what will happen? The effective gate capacitance will reduce. Now you can create this cavity in this SiO2 layer also. You will get the more or less same result. I will suggest to etch, to etch that SiO2 layer instead of this gate, because every structure has some mechanical stability. If we etch this part, then gate will be less stable. Instead, if we etch that SiO2 layer, then you might get some better result. That I will show you later. So this is the first version where we have etched some part of that gate. Gate consists of chromium layer and gold layer. We are etching that chromium part. And what will happen when we are etching this chromium part? Why we are etching this chromium part? Why not gold? Because look, hence we have a cavity. The surface of the cavity, the bottom of that cavity is SiO2. Here also at the bottom of that cavity we have SiO2. SiO2 is a good functional material to trap that biomolecule, because this surface functionalization, this is the most important thing of a biosensor. If your surface is not functionalized properly, then it will not be able, or this sensing surface will not be able to bind with that analytes properly. So you need to functionalize this surface. And if you have SiO2, sometimes SiO2 has porous nature, that can be extra added advantage. Besides, you can easily add AICTE layer on SiO2, and this can be used to functionalize that surface. Finally, you can trap that biotin septavidin, or you can trap that biomolecules inside that surface. So if you do so in gold, you will not get this kind of advantages. Here we are getting that surface. It is the bottom of that cavity. This is SiO2 layer. So that will be okay. So the thing is, here we are using some nano cavity, and inside this nano cavity we will trap that biomolecules. So there are three things. First, you have this kind of structure, without gap. Now we are etching some part of chromium to create that cavity, nano cavity. And third, this nano cavity will be filled by this biomolecules. Now look, when these nano cavities are filled by air, then dielectric constant is 1. Now, when the nanocavities are filled by biotin or septavidin, then the dielectric constant will be 2 or 2.1 or 2.3 roughly. So here we have some changes in dielectric constant. Why we are worried about the dielectric constant? Why we are considering this dielectric constant? Because we know if you have parallel plate capacitor, then the oxide capacitance, that will be epsilon naught A by D. It is the gap between this. A is the plate area and epsilon naught is the dielectric permittivity. Better if I say permittivity, epsilon naught. K epsilon naught, K is the dielectric constant. So in air, K will be 1. In biotin septavidin, presence of biotin septavidin, K will be 2 to 3. So what we can say, we can get different C, different capacitance. If we have different capacitance, ultimately that for threshold voltage, that minimum gate to source potential, which is required to produce that current, this conduction, that will be less. So what I want to say, when we vary that dielectric constant, then COX, oxide capacitance, will vary. When oxide capacitance varies, this will directly affect that threshold voltage, and finally it will get some variation in your current. So this is the most important thing, and this is the basic principle. Here we are using dielectric constant. That's why we can say this is dielectric modulated. Modulation means change. We are changing the dielectric constant of that oxide layer. So here, we are changing the dielectric properties of that gate, and finally we are getting some variation in total oxide capacitances. So here what we can say, this dielectric modulation, here we are involving incorporating dielectric modulation. So that is why this is dielectric modulated. This is a MOSFET, so that's why dielectric modulated MOSFET. We are sensing some biomolecules, biotin, septavidin, that's why biosensor. Okay. Now you can choose any other material instead of biotin, septavidin, but biotin and septavidin, this protein ligand combination, this has been used extensively in maximum literature, so that has been reported in so many literature. Now come to that point. What will be the impact on VI characteristic? That is the most important thing of this biosensor, because this is FET based biosensor. So obviously we will get some changes in current. Sorry, I'm not able to check that question and answer. Better if I finish this part and then I'll move to that question answer round.
Yes, you can continue. We will have question answer session. Oh, after completing your presentation, we will go for it.
Okay, fine. So
okay, continue, sir.
Let me go through this, because this is the most important principle of this dielectric modulated FET. So here we are measuring the impact on VI characteristics. Now look at this, that I was talking about, gate, gold, chromium. And here inside that nano gap, there will be some trapping of biotin and septavidin. So this is oxide layer, it has some capacitance, COX. How can we measure EOX by TOX? TOX is the thickness, EOX is the permittivity of oxide. If we consider SiO2, then permittivity will be 3.9 epsilon naught. So this is COX. And CSD, this is the depletion layer capacitance, because this channel will be depleted more or less, so this can be termed as depletion layer capacitance. I just have given some value. If we tap that biotin or septavidin, that value will be roughly like this. So what will happen? Look, when this part is open, I mean to say, in absence of biotin, septavidin, this capacitance will be less. I mean to say, there will be no portion of this capacitance. You can put some capacitance having less K. This C biotin has some values because of some dielectric constant. Now, if we consider some air only, then what will happen? It has some less capacitances. Now, these capacitances will be added in series. These capacitances are arranged in a series way, so we can find out that equivalent capacitance. The thing is, when this air, instead of air, when this gap is filled by biotin, septavidin, this C biotin and this CSTR, this is capacitance because of septavidin. This is the capacitance because of this biotin. This will come in picture, and that will change the total capacitances. So as we are getting different capacitances, ultimately what will happen? For same voltage, we know that Q is equal to CV. For same voltage, if different C is there, so Q will vary. If Q is different, then ultimately liquidity, that rate of change of data, I mean to say that current will different. I'm just putting some simple analogy, but inside that there will be in-depth physics. But I'm just explaining this as a thumb rule. So when this gap, when air gap is formed, then what will happen? K will be low because of low dielectric constant, K is 1. So total gate capacitance will fall, obviously, and VT shifts to a more positive value. Okay, look at this picture. This one before chromium age, black one. So this one is before chromium age. Okay, this is the current with respect to gate potential. Now this is red circle. This is after chromium age. So after chromium age, what will happen? That cavity will be filled by air, and that is why K will fall, capacitance will fall, threshold will shift by 0.7 volt or 700 millivolt. Okay. Now what will happen when this cavity is filled by biotin septavidin, then because of higher dielectric constant, then that capacitance will be more and Vt will shift towards left. Look at this. This green triangle, this is in presence of biotin. So in presence of biotin, this is minus 0.06. Why minus? Because that Vt is shifted in left side, 0.06. That is 60 millivolt shifting. Now again, this is biotin. If we add biotin and septavidin both, then capacitance will be more because these two capacitances are in parallel. So what will happen? That combined effect will be more. And look at that blue color. That combined effect is this 0.73 volt, 730 millivolt shifting is there. So this is the impact of VI characteristics. Okay, so this will give you that same picture. Before chromium age, you will get one current. After immobilization, I mean this is after combination of biotin and septavidin. And this red one is after chromium age. First black to red because of K is equal to 1, drastic falls, and then K will improve by 2, 3. That's why we are getting another blue line in between these two. So this is another impact on VI characteristics. Here, what we can say, when we add this biotin septavidin, that is the most one of the disadvantage of these things. What will happen when we add biotin septavidin? Then electron, you are providing, basically you are providing a current path for the flow of electron to the gate. Is not it? When we are trapping some biomolecules here, so electrons, these electrons will get some path to flow through it, and you are getting some IGS. So that is why when biotin and septavidin both are combined, you will get a large increase in gate current. This is a leakage current. You are getting into the -7 ppi, sorry, microampere range of gate current. It is disadvantage. Whereas when only you are dealing with air gap or that before chromium age or after chromium age, look at that current, but this is in the picoampere range. So this will happen. And here we are getting different kind of, I mean, it is a 0.4 micron chromium age, 0.2 micron chromium age. That means that length of that cavity that will vary. For 100 nanometer, for 200 nanometer, for 400 nanometer, you will get different amount of currents. Okay, so it depends on that cavity length also, because it depends, it must depend on the cavity surface. Length means there must be W, there must be L, so there will be some cavity sensing surface area. Basically biomolecules will be trapped on this surface area. So if the surface area is larger, then it can be able to trap much more biomolecules and you can get better result. But for larger surface area, you need larger dimensions. But when you are dealing with nano dimensional structure, the sensing surface would be nano dimension. So here, this is another thing where you can get that biotin septavidin binding. You can break that biotin septavidin binding. This is some reverse operation with non-ionic aqua solution. And if you expose this to a temperature 770 degrees Celsius, then you can get almost previous structure. Okay, this is that after chromium age, that red one, and this circle and this triangle, this is recovery, after recovery. I mean, it is after that high exposure, or when we expose this to high temperature, then you are getting this kind of thing. So these two are more or less same. So there are possibilities to get that previous one. Okay, this one is now I'll just go through these things a bit quickly. So this is silicon nanoribbon structure. Here nano ribbon means that length, there will be length of micrometer. I mean to say 3 micrometer length, but that width is very small. Look at this, 80 nanometer. That's why it looks like a ribbon. It's a silicon nanoribbon biosensor. Hence also we are using septavidin as a target molecules and biotin as a receptor. So this biotin septavidin bonding, that will be protein ligand bonding, as I've mentioned in last papers. Here also we are using that AICTE just to provide that NH2 along with that SiO2. And PBS buffer solution, that phosphorus phosphate buffer solution, that will be used also just to through that microfluidic channel. Okay, almost similar structure, almost similar principle. Hence, the structure is based on liquid environment. What does it mean, liquid environment? I mean to say you can put some, you can create some chamber. I mean to say if we add that pressure, I mean to say if we increase that pressure vertically, so what will happen? A chamber will be formed here where you can put some analytes, okay, and you can sense the biomolecule. You can sense that analytes using that similar structure. This is in wet environment. That's why we have some diffusion capacitance. There will be some diffusion capacitance in this case, but obviously the diffusion capacitance will have very high value at low voltage, because at low voltage this lambda will be very small. I mean to say that Debye-Hartley length, that skidding length, that will be very small. So ultimately E water, that is 80, close to dielectric constant is 80 epsilon naught. So that's the difference will be very high. You may consider this value. Look at this diffusion capacitance for 1x buffer solution, 0.1x buffer solution, 0.01x buffer solution. The value is 95.2 for 1x buffer solution compared to that other capacitances. Now, what will be that equivalent capacitance? When you find out that equivalent capacitance, say 1 by C equivalent, that will be 1 by CSD plus 1 by COX plus 1 by CAPTES plus 1 by this combination. Now here, as CDF is very high, so 1 by CDF, that will be very low. That we can ignore. And here we are getting some relationship between that concentration and that output response, because this one is another important feature. Last one was on dry environment. Now this is on wet environment, where the target concentration that matters. Look at this, 0 picomole. Because of this low concentration of analytes, very few biomolecules, almost 0 biomolecules were there. No biomolecules were there. But now if we consider 1 nanomole of concentration, what will happen? Some plenty of biomolecules are present. So the challenge is to detect the biomolecules at femtomolar range or at picomolar range. If the concentration is at nanomole range, you can easily detect that biomolecule. There will not be any credit of your biosensor. But if you can detect that biomolecules at the femtomole range or picomolar range, that will be the most important things, because if you go through that level of detection, there are too many diseases where level of detections are lying in between attomole to femtomole. So you have to prepare your device in such a way that you should be able to detect that attomole range of biomolecules. So here that equivalent capacitance are there. Using this picture, look at this depletion capacitance. This one is oxide capacitance. This is silane group that will be formed when Si will react with water. Then AICTE with that Si-NH bond. This is AICTE, capacitance is AICTE, and this is for biotin, that total capacitance. Diffusion capacitance should be there because we are considering some wet environment by continuing this experiment in wet environment. Hence, also for septavidin, C diffusion, and this is septavidin, then AICTE, C of CST. So if we consider that overall capacitance, as I have mentioned, it will simply look like this. Now here, another important thing is this SS is subthreshold slope. Now, if you have better subthreshold slope, that means your device is responding quickly. And if your device is responding quickly, that means you need less response time to get that final output, to provide that final output. So some of these SS must be related with that response time. And that's why TFET is very much effective compared to that MOSFET, because TFET has low SS, a better subthreshold slope, so it can give that results within this time. But this is not that, I mean to say, this response time it not doesn't depend on that SS, does not relate with that SS only. There are too many parameters, external parameters, which can influence that response time significantly. Even sometimes pressure and temperature, that will come in pictures too. So here, this is the current response for different septavidin concentration. Look, as I have mentioned, if you have very high concentration of, I mean to say, these are low concentration, 0 picomole to 1 nanomole, but compared to 1 nanomole, 0 picomole is less concentration. So the device is able to detect that biomolecules at that low concentration. And this is some SS. Hence, you get another thing that SS degrades with that septavidin concentration. I mean to say, if your concentration of ceftazidime is more, then your subthreshold slope will degrade. That is known as SST effect. Actually, this is related to some depletion capacity. This is related to that depletion capacitance. There will be some change in value in depletion capacitance if you add more ceftazidime. So ultimately, your sensors will degrade. There is a term alpha. Alpha is binding coefficient. Now, this one is very important in biosensing, but if you go through that literature, then very few works have been concentrated on that binding coefficient. Binding coefficient means how efficiently this biotin ceftazidime they are binding with that AICTE, or how ceftazidime and biotin are binding with each other. Or basically, this is related to that immobilization. When a proper binding is occurred, then that biomolecules will be immobilized and they can help to produce some signal. If these biomolecules are not immobilized, if they are not binding properly, then you will not get a proper signal at that output. So binding is very much important, and that's why you have to functionalize the surface properly. Okay, just I'm going through these things in brief. Say this is our this is one of our structure which has been published in TED, surrounding gate MOSFET biosensor. Hence, instead of planar structure, we have used surrounding gate. Now, here we are checking the different issues when that cavity is filled by biosensor. First, we have optimized this device depending on that on-off ratio, subthreshold slope, DIBL, and on basis of these things, we got this LG by LUND, that is underlap length, and LG is that gate length. This is LG gate length, and this LUND, this is underlap length. So we got these things when LG by LUND, L underlap, this is 2, then we get better characteristics of that device. Once we optimize this device, we concentrate on that biosensing operation. And here also we etch that gate and we fill this gap by some biomolecules. And finally, we got this kind of responses. In presence of positive biomolecule, in presence of negative biomolecules, what will be the variation in threshold voltage that we got, that we obtained? Say for full, half, quarter, that means when the cavity is full filled, then we get better response. When the cavity is half filled, we get less variation in threshold voltage. The minimum is for quarter filled. Obviously, for quarter filled, that the dielectric constant of that biomolecule, I mean to say, this gap will be very less. This gap will be very less when it is quarter filled. Suppose this gap has that thickness is 10 nanometers. So when it is quarter filled, then 2.5 nanometer part has some dielectric constant of 2, and remaining part has dielectric constant of 1. So overall capacitance will be less. And also another thing, when you put too many biomolecules inside a small gap, there will be an issue which is known as steric hindrance. I mean to say, look at this picture. Say this is sensing surface. These are the, say, DNA, and this is some kind of antibody. And if the size of that antibodies are more, then there will be some repulsion. One biomolecule will not allow another biomolecule its close vicinity. So that's known as steric hindrance. So what will happen when this sensing surface is close, when the surface zone, when it is heavily crowded, then that will affect that binding also. One biomolecule will hinder another biomolecule to bind properly. And this sensing and this steric hindrance, this will increase with that size that is given in kilodalton. So here what will happen for that DNP biotin, as the size is less, that steric hindrance will be less. So more binding will occur, and finally we'll get more current. But look at the 16-base DNA. Look at this anti-dinitrophenyl IG. This is some kind of enzyme. So what will happen, say, for this dimension, we are getting less current because of higher steric hindrance. If the gap is less, steric hindrance will be more. If the gap is more, then what will happen? Then steric hindrance issue will be less. Now, this is the most challenging issue in these sensors, nano sensors. When you consider a FET-based nano sensor, we are dealing with some nano-dimensional sensing surface. So the gap between successive biomolecules should be very less. Now, instead, if we consider very large gap between successive biomolecules, so what will happen? you will be able to trap only 2 to 3 or 4 to 5 biomolecules. Now, is it okay with your sensors? Will it be able to detect these biomolecules? If it can, then fine. But in general, this biosensor won't be able to detect such biomolecules. So that's the problem that steric hindrance issues impose limitation or challenges on these nano-dimensional biosensors. It's not a case it's not the case of MOSFET based biosensor. This steric hindrance induced sensitivity degradation, that is the picture or where you are dealing with some biomolecules. So it can be observed in case of pH sensors also, or it can be observed in dry environment and wet environment also, where you are placing two biomolecules very close to each other. So this is one graph where current is degraded in presence of antibody, because in presence of antibody, the steric will be more, steric effect will be more compared to that in absence of antibody. So you will get less current. Similarly, look at this change in current with respect to time. Also here we have septavidin, and look at this change in current. So I just want to point it out one thing, that steric hindrance is very much significant. So here also effect of charged biomolecules. How did you consider? How will you consider effect of charged biomolecules? Some biomolecules are charged, some DNAs are negatively charged, some RNAs are positively charged. Even if we consider COVID coronavirus, they are also charged. So here, what we have done, we have incorporated interfacial charges or interface charges, and these interface charges, they can be positive or they can be negative. So basically in device, what will happen, that sensing surface is on SiO2 interface. So when that interface charges are at that SiO2 or the charges are at that SiO2 interfaces, they will change that VFP, flat band potential, because flat band potential is QNF by Cox, where NF is that interfacial charge density. So when VFP changes, this will change that threshold voltage. When threshold voltage changes, this will change that current. So ultimately, we'll get some different current. Okay, so here we are getting some 25 millivolt of change in threshold voltage instead of 10 millivolt. 10 millivolt, we have obtained this 10 millivolt in case of conventional. And we also measured that LOD level of detection, which was 134 attomole, and that was quite significant, because if we use this device, if this nano dimensional structure can offer 134 attomole, that is good one. Okay, I just want to highlight this one. This one, I just want to close that session as soon as possible. This is junctionless level fed biosensor. Why it is junctionless? Look, there is no PN junction. This is source drain, highly N plus type, highly doped N plus type. Channel is also N type. So this is basically junctionless MOSFET structure. Same principle, but here because of that steric hindrance issue, just we have published this paper in again AICTE. Because of the steric hindrance structure, steric hindrance, we have considered the biomolecules in different way, because inside that cavity, biomolecules can organize in a random way, but during simulation we couldn't consider that random organization. Instead, we have considered some increasing, decreasing, concave, convex, this kind of shape. And if the biomolecules are organized in this way, I mean to say, if these biomolecules are organized in this way, you will get better sensitivity, because as that biomolecules are crowded in this source channel interfacing, it will enhance that capacitive coupling. It will improve that capacitive coupling. Ultimately, you will get better sensitivity, and you will get this kind of things. For Staphylococcus nucleus, we observe this kind of things. We get significant del ion, del VTH for this combination. Here, I just want to show that biofed circuit. How can you convert that current into some how can you generate that final message signal? Say this is a biofed. Okay. Now, what will happen in presence of some biotin or septavidin? Say K1 is here in K1 is here, and 2.5, 4, 8, 10. You can consider this as DNA. This is some enzyme. This is 2.5. Say septavidin combination. So what will happen? This is VDD, some resistor is kept here. This is the CL. So when this device is on, ultimately what will happen? Some current will flow through this. Some voltage will be drop across this. This drop is known as VR. Okay. Now check the voltage value VR. When it is 1 in absence of biomolecules, then that VR is 77 millivolt. But when we fill that gap by some DNA, gap is only 1 to 20 millivolt. There is a change in VR. Now, if you put some differential amplifier, you can enhance that gap or enhance that level, and then you can put some, say, A to D converter. Then you can get digitized data. Okay, so interfacial trap charges. If we interface trap charge in presence of interface trap charge, look at the changes. When we are considering neutral biomolecule, then VR is 45 millivolt. But when you are considering negative and positive, 72 and 25. Also, you can calculate that negative biomolecules. This device is sensitive to negative biomolecules compared to that positive, because this will change that VFB more compared to this. Better than conventional, as I have mentioned. This is the graph just to show that. This paper we have published in IEEE. I'm just skipping this. This is tunnel fed biosensors based on same principle and sensitivity. This one is that threshold voltage sensitivity, but I'm just skipping this thing, more or less same operation. I just want to show this thing. This is silicon nanowire MOSFET, where silicon nanowire and MOSFET, these two have been fabricated on a single device. This one is challenging, and this is the one step ahead to that. I mean to say, if we can fabricate this systematically, then we can fabricate that. We can go with that LOC concept also. And here, although you will get some variation per pH variation. Average threshold voltage variation is 52 millivolt. There is a NOTS limit, which is 60 millivolt, so it's very close to that NOTS limit. With VH, that current changes from 10 to the power 8 to 10 to the power minus 10, though the current is less significant, but that concept is very good. I'm skipping these parts. Okay. What are the future scopes? There are too many future scopes of this biosensor, but I just want to point out one or two which are very much challenging. Say, obviously, when you incorporate that electronics and biology, you need to know electronics as well as biology. Technology is required. I don't have very good knowledge in biology, but sometimes we just need to go through some paperwork, or we just need to go through that paper to get some concept. Otherwise, how do you able to design a biosensors? The most important one is that steric hindrance. That steric hindrance, as I mentioned, that steric hindrance, it will not allow another biomolecules in its close vicinity. So when you design that nano sensor, when this biosensor or the biomolecules are placed very close to each other within few nanometer gap, then what will happen? Steric hindrance will be more. So you can't consider high concentration for nano-dimensional surface. You have to go with low concentration. And if the low concentration is low, then the challenge is LOD. What is your LOD? Will you be able, or will your sensor be able to detect that biomolecules within that femtomole concentration? Is it possible? If yes, if you can do, then fine, okay. Otherwise, your sensor will not work, because then you have to increase your dimension. And if you can, if you're increasing your dimension, then if it is more than micrometer range, then it will not be considered as nano-dimensional structure, and there will not be, and then the structures will not be applicable for implantable or for some wearable devices. Now, integration of microfluids plus FET. Microfluidics, this is very good. And if you can incorporate that FET, because too many circuits which you need to fabricate along with that microfluidics, so this compatibility should be there, then we can go with that LOC. Selectivity, sensitivity, you have to check, because it's not like that you are detecting one virus at a time. There will be plenty of similar virus, because with coronavirus, there might be some influenza or some common flu cold viruses. So you have to isolate that particular one from this mixture, and you just need to check your device also. What we have done in a hurry, we just concentrated on a single virus or a single element. We didn't check what will happen when a mixture will be there. So that we have to check. Otherwise, you can't say anything about the selectivity of your device. Incorporation of 2D material in sensing, that is a good thing. Nowadays, that channel has been replaced by that graphene or some other 2D layers, and we are getting very good results at very low voltage and low concentration. So these are challenging, but parallelly we have to check that compatibility or feasibility of these circuits. Also that toxicity of these materials, because if you devise a nano-dimensional structure, if it can sense the materials with good sensitivity, this should not be the end. You just need to check that toxicity of this element. If the device is non-toxic, then you can go for that implantable device fabrication or implantable device implementation. Otherwise, this is not possible. And that's the end. Sorry for tolerating me for almost 2 hours. If you have any
I have a
question.
very small question, sir.
Okay.
Sir, am I audible? I have a small question.
Yeah.
Yes, you are audible. Welcome.
Yes. Sir, actually, I heard that there is an emerging field on quantum biofluid chip. So my question is that how the quantum information is actually carried out or processed in quantum biofluid chip. So as we know that the quantum bit informations actually carried out in actually a photon particles, orientation or spinning of photon particles. But in biofluid chip, how the quantum information is carried out? This is my question.
Okay, look, this is not actually my research field, that quantum biofluidic. But I just want to say one thing. It's not like that quantum information processing. Here we can use some MEM structure, nano-dimensional MEM structure, and this nano-dimensional MEM structure that can be used to pass that microliter liquid or microliter amount of samples. Basically, the function of biosensor is to detect or to pass that microfluidic or to pass that samples. Suppose if we consider, let me go through this thing. Say, this is an example of that microfluidic chip, and if you observe these things, here you will get, this is the microfluidic chip, and here you have valve, pump, mixture. These are all based on MEMS, and these things are used to pass that liquid, nano-dimensional, so NL amount of liquid, nanoliter liquid, you just need to pass through this microfluidic chip. So here the dimension is nano dimension, and actually here you are not passing that phonon, you are passing, when you are dealing with biosensor, as per my knowledge, you are passing that liquid, so passing that samples, because then the samples will be processed. After detection, there will be some signal transduction or signal conditioning unit that will finally transform your signal.
So there is no digital information are processed.
No.
According to you, there is no digital information is processed.
No, as per my knowledge suggests, I don't think there will be processing of digital signals. Basically, microfluids, that means, or that microfluidic chips, these are used to pass that samples, that nano-dimensional samples that we need to process. Suppose you are injecting some medicine in inside. You can get some implantable devices inside your body. The function of this device is to inject that medicine after regular time interval. Can you turn off that microphone?
Prem, kindly unmute. Some noise is there.
Yeah. I'm getting too much noises.
Yes, sir. I heard some background noises are there somewhere else. Not in my side. Not from my side.
Yes,
So
okay,
it's okay. So the thing is, so, I don't think that is quantum information processing. That is basically.
So there is okay. I understand. So there is no digital information is processed or carried out in the silicon chips.
As you are mentioning microfluidic chip for sensing application, for biosensing application, look, there might be some other aspects, but as we are dealing with biosensors, if you are considering microfluidic chip, the primary objective will be just to pass that liquid or that nano-dimensional nano that you have to inject somewhere, that you need to pass it.
Okay, thank you, sir. I got my answer.
Thank you, Donmoy sir. for interacting. So there are some questions in the question answer chat box
Yeah,
from Ashok
to
Nath.
detect, yeah, Ashoknath, first to detect the presence of bacteria in patient's body, how you have to use nano sensors. Look, you can use that FET based nano sensors, but first what you have to do, you have to collect the samples where bacteria is there. I mean to say, suppose you are collecting some blood samples, bacteria are there, then you just need to uh, put that samples in some cavity, and if you are getting some VI characteristics change, that will highlight the presence of bacteria. That can be done. Say, so for example, you can do same thing for virus also. Virus have 6 to 8 dielectric constants. If you know the dielectric constant of that specific virus, then you can say, okay, if virus is present, then VI characteristics change will be something like that. And if you are getting this kind of changes, you can say, okay, virus is there. Do we need a
Okay,
medical
thank you,
doctor or
sir.
a nanosensor expert can do experiment? Look, if we are doing this manually, obviously doctor is required, but once you can prepare your device and if you can incorporate some algorithm empowered by AI or ML, then you know, I don't think you need a doctor. Can you use nanosensor to detect blockage in our heart? I have some doubt. Actually, I think imaging will be the best thing to find out this blockage. Or if because of blockage, if there is any change in protein of your, I mean to say, if there is any change in your blood protein, I mean to say, suppose it might be possible because of some disease, because of some blockage of your heart. Say, suppose X protein or Y protein of your blood is changing. Now, if you know this and if you measure that protein and if you are getting any possible, I mean to say, if you are uh, you can get some confirmation from this way only. Otherwise, direct using nanosensor, I don't know that actual process. And the last thing is to detect presence of coronavirus, how much time is needed to get positive result using biosensors? Look, if we go with that graphene based biosensor, hence I just have give one example of this graphene based biosensor. So these things, suppose here that response time depends on one thing. You have some graphene surface or sensor surface. Now you are adding some swab or you are adding some samples. These biomolecules that will move through that sample and will reach to that surface. This is one mechanism that is external. I mean to say completely external. No one, basically that electronics engineer are not dealing with this thing. But this will take some time. That entire process will take some time. But after, say, suppose now biomolecules are very close to that graphene surface. Now it will take some time to form that bond. For complete binding, there are too many aspects. If there is any steric hindrance issue, then what will happen? They will hinder each other. If your surface is not properly functionalized, if your receptors are not very good, then they will not be able to form that covalent bond. So what will happen? Ultimately, these things will affect that binding mechanism. If the binding is smooth, then what will happen? That sensors or sensor surface can bind with too many biomolecules within a small amount of time, so response time will be smaller. But if your surface, suppose if your surface is not ready to bind with the sufficient number of biomolecules, or might be your concentration is very low, you are not getting too many biomolecules to get that equilibrium condition, then response time will be very high. It will take too much time. Okay.
Again, Ashok Nath raised his hand. Sir, please.
Yeah, you have answered all my questions, but still I have one doubt. The doubt is like your sensor can only detect the virus, the presence of the virus, but can it detect the what exactly the virus I have in my body, like whether
That
it's
is
a coronavirus
selectivity.
or some other virus, or it can only say that I have got attacked by some virus.
No, look, that is not, I mean to say, you won't be able to find out all the virus or their composition of that presence is within short span of time. I mean to say, using this kind of sensor at this moment. The thing is selectivity. First thing is which one is dangerous. Using this sensor, I mean to say, at this moment, using this sensor, you can identify the most dangerous one. Suppose you want to identify that coronavirus, and obviously coronavirus has a larger dimension, so it has a higher dielectric constant, so it can be detected easily using that PET sensor. So it can impose some very good changes. It can change that DI characteristics significantly. But say suppose in association, say with that coronavirus, you have some MERS virus also, or common flu cold virus also. But I don't think using this technique you will be able to find out the other competition perfectly.
Yeah. That's why I'm worried about that. It can only give
No. There is selectivity. Basically,
you have to go
this.
for RT-PCR test.
Yeah. Then what you have to do, you have to just eliminate then coronavirus, and then with these samples you have to find out that dominating one.
Yeah. Thank you very much.
Thank you, Ashok sir. Okay, if any question, participants, if you have any questions, you can raise your hand or write in chat box. So I think there is no more questions left. So thank you, sir. Thank you for your nice and informative presentation. I'm requesting Prem to kindly display the token of appreciation. So thank you, sir. This is a little token of appreciation
Thank
from
you
our
very
end,
much.
and hope we'll have your time in future also.
Sure.
And thank